Sure, yeah. So, hey guys, hello everyone. I'm Anurag. I work at Dgraph Labs and we develop an open source distributed graph database. And this talk is going to be about not a database, but a cache. So, Ristretto. So, yeah, so maybe I think I'll just dive right in and we'll take questions later. Cool. So, Ristretto is a high performance Go cache. So when we were developing Dgraph and we were benchmarking it against different data sets, we found that Dgraph was not as fast as we expected it to be. And what happened incidentally was when we were trying to test our key value store, which is Badger, we kind of did a commit to remove the cache library, group cache is LR cache, and then that increased our throughput like 5 to 10 times, and that was like really surprising to us because cache in itself is there to increase your throughput, right? And but disabling the cache increased our throughput. So then we went into like what was going wrong, and is there a better way to develop a Go cache, and what we could be building. Yeah. So we looked at the state of the art of the other Go cache libraries available, and then we figured out that it's not there is no particular tool which has everything which we needed, and there's a separate blog post which I can link to afterwards how we evaluated. But in precisely our requirements were like the data, the cache has to be concurrent so that like different Go routines can access it, and you can scale it with more cores. It has to be memory bounded so that you can specify that this is the maximum memory that your cache can take. It should scale well with the number of cores and Go routines. Then it should also scale well with the non-random key access distribution. So in any cache specific workload, the key distribution is not uniform, right? Some of the keys get accessed exponentially more times than the other keys. So your cache should perform better with this non-random key access distribution. And of course, if you are building a cache, you try to have as high cache hit ratio as possible. So these were our 5 requirements, and we started building Ristretto. Okay, so how did this name come about, Ristretto? So how we like to think about is Ristretto is like the better part of espresso. So it's smaller in size, but it's stronger in content, and that is what our cache also tries to be. So it's very lightweight, but it's very fast and very efficient. We do have to make some trade-offs, and we'll go into that. But yeah, that's how we like to think about our cache, like Ristretto. So how do you use Rcache? So this is like the basic Golang code which you would need to start using the Ristretto cache out of the box. So you declare a cache here. There are 3 configurable parameters. One of them is num counters, which tracks the number of keys for which you would track the frequency of. I would get into detail how this affects your cache's performance. Maximum cost is the maximum memory size you are allowing your cache to have. Buffer items is again a number of keys per get buffer. We'll get into what that configures. So once you define your cache, you just do a set. You wait for some time, let the set value to pass through the buffers, and then you do a get cache get key, and then you print the value, and then you delete if you don't want that key any longer. So like very simple, as you would expect any cache to work, right? So you declare a cache, set a key, get the key, and delete the key. Cool. So suppose you want someday you decide you want to make a cache of your own, right? So how would you go about it? So what are the basic, like 3 very basic parts of any cache? First of all is a store. So store is essentially the storage of the data which you are storing in your cache. How would that storage work? Which data structure would you use to do keep that storage? Second is cost of the key. So can you do some optimization while storing key value? So that is also part of the store uh, box, how I like to think of it. So there is one store. Then the second is policy. So policy is how do you make decisions when to add keys, when to evict keys, and based on which what conditions. So one of the most used policy is LRU, least recently used. So when your cache fills up the size, you evict the key which is like which was least recently used. So that is policy you have to decide. And the third is, if you are making a concurrent cache, you have to take care of the thread contention and the performance bottleneck that and comes because of contention. So that is like the third part. So whenever you start making a cache, you think about store, policy, and the concurrency. Let's get into the detail of each of these. Cool. So in terms of storage, what we ended up doing in Ristretto, like instead of storing key value, we store a hash of the key. So we generate a hash of the key using runtime mem hash, and then store that hash with the value. So your keys could sometimes get very long or very uh, bulky. So to save on that, you use a hash. So one caveat here is that currently it won't handle collisions at the moment. So yeah, so if there are two key value pairs where your hashed value collide, it is possible that it would return you the value of the other key rather than the one which you searched for. So yeah, that is kind of one trade-off. But what you save on is the memory footprint as well as the complexity, because your data transfer reduces. So we use hashed keys. Yeah. In terms of actual storage, so once you decide that, okay, this is the keys and this is the values, or maybe the hashes and the values which I want to store, you want to decide on what actual data structure you want to use. So there are quite a few possibilities. One of them is like you store it in like a usual map and keep it under a log map, so that whenever any thread tries to access it, it acquires a log and releases it when it's done with it. Then the other option is sync map. And yeah, so but what really worked for us was, so both of these, log map and sync map, suffer with contention, because you would be lock contention. What you would really be like, your threads would really be competing against each other to get those locks, etc. Right? What really worked for us was logged map with 256 shards. What we did was that rather than having just one map, we were, since already hashing our keys, we took it a one step further and we divided those hashes into like 256 shards, so that your contention comes down a little. So yeah, so each shard has a separate lock. So that's what we use for our storage. In terms of cost of keys, yeah, so generally in caches, every key value has a cost associated with it, which is usually one. In Ristretto, we give the user an option to have a different cost associated with the key value pair. It could be the length of your key, or it could be just the usual one, or it could be anything, or the length of the value. So, and this particular cost of each key value pair is finally used to calculate whether your cache is running out of memory or not. So it's not like just the number of key value. It's basically the cost which is added every time you add an element, add a key value pair, and that is what is being, that total cost is the capacity of the cache. So the number which you sent here, the max cost, that is what this goes on to add to. Cool. So yeah, so in terms of storage, I discussed about storage and the cost current. So now we move on to policy. In terms of policy, we there are two main ideas here. One is we improve the hit ratio by not admitting every item, and the second is you evict based on least frequently used instead of least recently used. I'll explain what the first item is, like improve hit ratio by not admitting every item. So what happens is, like, first, if you see like one key, and all of this, like both of these points come into play when your cache is full, right? If your cache is empty, then you anyway like just add it to you. Why would you want to keep your cache empty? Both of these points come into play when your cache is full, and now you have to decide whether you want to add this new item, and if yes, then which item would you want to evict. So if you see a key value and this is like the first time you see it, then we propose that let's not add it to your cache, because it's possible that it might not never come back again. So then you will be just evicting other items which were more frequently seen from your cache and could they have better chances to be seen again. So that is why you have an admission policy in place for Ristretto. In terms of eviction, so suppose you see this key which you have seen few times already, and this is not the first time which you see it. Now you want to free your cache to insert this. So now which keys would you want to delete? In there as well, we see, okay, so these are the X number of keys which are least frequently used. So let's delete them. Let's delete the least frequently used keys and then add this new key, so that, yeah, so that is what becomes our policy. So in terms of so these are the two main ideas. How do we implement them is basically these two features. One is doorkeeper. In doorkeeper, we use a bloom filter to check whether the key is seen before or not. So for those of you who don't know bloom filter or can't recall it, it's just like a simple data structure to deterministically say that this key is not in the set, but if it says that it is, then it could or could not be. So it's a probabilistic data structure in a sense that you can rely on the negation but not on the positive affirmation. So we use bloom filter, and it's like space efficient and time efficient. That is why we use this. So we use bloom filters to check whether this key has been seen before or not. If not, then we are more concerned whether if it's not been seen before. If not, then we don't add it to our cache. And TinyLFU is again like a small algorithm. You admit a new item only if the estimated frequency is higher than that of the item being evicted. So like I said that here, evict based on least frequently used. So ideally what we could have maintained was like a min heap of the frequency, right? But that becomes too cumbersome to maintain and handle. So this is some approximation of LFU, which is TinyLFU. So you say that, okay, so this is the key I'm getting, and you have the frequency of this, and now the items which you will be evicting, if you evict them only if the frequency of the incoming item is more than the items being evicted. So again, to implement this, we basically need a key frequency of access map, and that is stored using a count min sketch data structure, that which is also like a probabilistic data structure, very similar to bloom filters. In all of this, we are also trying to maintain the recency of the keys which we see in some sense, right? So what we do is that, okay, so you have processed 9 keys or like n keys, and now you divide all the counters by half every n iteration, so that some particular key value pair which you had seen earlier but haven't seen for a while would decay out in some time, so that you have some form of recency also embedded in your algorithm. So so this is like the small pieces of code how we implemented it. So if you see here, you get the key, and this if condition is your doorkeeper. If it is uh, able to add, then if it is able to add this key in the bloom filter, that means that this is the first time it is seen. So you don't increment the frequency. And how does that help? Because frequency is at the end what is being used to determine whether that key gets added or not, right? So if you have not seen it before, you just mark that it is not seen, but you don't increment the frequency. And if you have seen it already, then it won't get added, which means that now you have to increment the frequency. So yeah, so that is the doorkeeper part of it. Now in terms of the second part, the TinyLFU, here, so you suppose this is the incoming key, and this is the incoming estimated frequency of this key, which we would have updated sometime here, right? Now you have this incoming hits, so you keep on evicting your cache till the time you don't you have enough room, and you only add if the incoming item isn't worth keeping in the policy, you reject. So basically here you check that the items which you would be ending up uh, evicting, if their frequency is greater than the incoming frequency, then you don't add the incoming, you just remove, you drop that incoming key. So that is the tiny LFU for you. And this is also based on one of the papers which I've linked there, you can check. Okay, so now we have talked about storage and policy. So we go on to the concurrency part of it. So in concurrency part, we also used, we again went to literature and checked out this cool paper. It tells you method to kind of remove contentions between threads by batching up the updates which are critical to your thread contention, right? Those updates which are in your critical path, and your process will just stop unless they happen. So the idea is not have every update all the time. You store those updates, and then you acquire the lock once, do all the updates in a batch, and then you release the lock. So that way you are acquiring less number of locks, and you are reducing the contention. The idea, so that is the main idea. You batch up the updates to the cache. And how do you go about implementing? You use again like a cool data structure, ring buffers. So when you getting the updates which you have to do in your critical path, you keep filling them in a ring buffer, and then you drain them once that buffer is filled up, and at that time your thread acquires the lock. So this ring buffer is configurable here, which I mentioned, right, in the buffer items. So that is the size of the ring buffer which you would have. So the more the size, the more it will wait for the greater the ring buffer size would be, and the greater time, lesser contention it would face, right? And then number of counters here, I should also mention, is for this count min sketch data structure, basically the number of keys you want to track frequency of. So when you this key frequency is for all the keys which you see. So that is what the first parameter there was. Yeah, so you use ring buffers and you drain them when filled into critical sections. So what are the critical sections here, right? So let's see gets. So whenever you get a request of get particular key value, so that is immediately served, that is not stopped. You are not stopping it. You are not filling that get request into a buffer. What you are filling in the buffer is the frequency update, because that can happen in the background, right? So if not, if suppose you didn't have that batching, what would happen? The data structure which you are keeping to keep the frequency of each of the key and the value, key and the frequency which you are storing in, then each get would acquire a separate lock on that data structure, update the frequency and get back, right? But here we are saying you can serve the get request by like at the time itself, but the updating the frequency in that data structure can happen in the background. And yeah, so that is what we keep in the buffer. So whenever we get a get request, we serve the request, but we also add the frequency counters in the buffer that can be drained into that particular data structure. And you use sync pool to maintain buffer. This gives faster performance than channels. So we tested like channels as well, but sync pool was giving us better performance. So gets hit increments are processed with a delay. Like I said, right? You serve the get request, but the increment of the frequencies are processed with a delay, and they are processed only after the stripe reaches its capacity, which is the like your ring buffer is full. So once the stripe is full, all the keys are pushed to admission policy. What this means is now the policy, which was keeping track of that frequency data structure, updates that data structure. And this is like a lossy buffer. because lossy because of two reasons. One is your garbage collection, like GC can kick in and it can remove some ring stripes. And the second, if there are too many pending calls in your sync pool, then they would get dropped, right? But that is kind of fine because first of all, you are not dropping the data, you are just dropping the update to the frequency. So maybe your data structure, which is maintaining key value frequency, is not entirely correct, but the data which you are serving is correct. And also the application which is using this cache should not suffer because there are too many pending calls, so the throughput increases. So that is for the gets. For the sets, the requirement is different. So set is like you are inserting a new key or you are updating an old key with a new value. So set requirement is different from get. Here we cannot actually wait for the ring buffer to happen, to fill up, because then it defeats the purpose of cache, because what would happen is that you would have a stream of numbers, key value pairs, which are not yet set, and then the users would not get them when they do a get query. So here we use channels. So so how that works is you get set request, you put them in a small buffer, and then you have channels which are continuously processing that buffer and updating that policies data structure with that. So here also there are caveats. So the thing is that when you get a set request, the thread returns and puts it on the buffer. So thread doesn't know whether that particular item was rejected or was it actually put. So you could have drop sets if the buffer is full, but or the policy rejects it. So you could have sets which are not executed, so to say, right? So that is kind of like and that would impact your hit ratio, right? So that is one trade-off which we had to do. So in terms of while reducing the thread contention. Cool. So this both of these items, like this ring buffers while get, and then using channels into a smaller buffer for sets, gives us makes our cache contention proof. So both gets and sets would drop items if too many are pending. Because it drops item, it performs really well under contention. The hit ratio is affected, but still it performs better than others. Yes, so caveats, set can get lost, but you never get an old value, because if set was called and the key was already there, you just update and you just bypass all this path. So you never get a stale value, but it is possible that a new key value is not registered even though it was set. Yeah. So total capacity of the cache is based on this cost. Okay, yeah, that is fine. And the benchmarks, right? So hit ratios were measured during Damina's Grexy's cache test along with our own benchmarking suits. So here are some of the results. So this is on the hit ratios for the search query. And this is the capacity, right? So if you see this is the Ristretto. It performed better than Go. Then this is your group cache. This is your free cache, fast cache, and big cache. So this is your hit ratio, and this is the capacity. And the particular data set, the trace described as the disk read accesses initiated by a large commercial search engine in response to various web search requests. So that is how the trace is described here. This is another database benchmark. So this trace is described as our database server running at commercial site, running an ERP application on top of a commercial database. So here you see Go performs slightly better than Ristretto, and then this is your fast cache, free cache, and group cache. Here's the capacity, and here's the hit ratio. Okay, so the throughputs. So all throughputs benchmarks were run on this configuration. So the load is mixed 25% writes and 75% reads. Here and on the x-axis you see the number of Go routines and the million operations per second. So here if you see your Ristretto quickly jumps up in the throughput and then stays stable as the Go routines increases, and it like performs better than the other caches which we benchmark it against. Yeah, again, similar for the read workload and the write workload. Yeah, so I think that was the overview of Ristretto, and yeah, I'm happy to take questions.